All right, everybody can hear me? All right. I would like to thank the organizers for inviting me. It's a great pleasure to be here. And I'll talk about joint work with Tal Amir, who was my PhD student, and with Ronen Batzli, and it will be about sparsity. And I don't know if Peter knows this, but he had a major non-sparse influence on my work. As I started my first steps into statistics and high-dimensional statistics, I remember this clearly. I had some idea about something, and I talked with David Donahoe, and he told me after 5 minutes, you should read this paper by Peter and Lisa, and I read it, and indeed it was somewhat connected to things that I was doing. And later on, I started thinking about covariance matrices. And again, Lisa and Peter were way ahead of me. They had amazing papers about covariance regularization by thresholding, but with Ian Johnston and others, we still were able to do something about sparse PCA. And of course, there was a paper by Sasha and Yangi and Peter on sparsity, and actually papers by many other people here. But in 2010, I was here on sabbatical with Peter, and we had many discussions on various types of sparsity. And yeah, it took me about 10 years or more, but I'll talk about sparsity today. Okay. So the talk will be about something that I think essentially maybe everybody here has worked or has heard about, sparse approximation of best subset selection. The problem setup is very simple. There is a design matrix A. There is a response vector Y. Someone gives me a sparsity parameter K, and I would like, in principle, to solve this problem. I'll call this P0, okay? Because I have a requirement that I'm looking for a vector that is exactly k-sparse. Okay. So this problem appears in many different contexts. One is in signal image processing or harmonic analysis. Y is typically your sampling of some signal. A would be, it's called a dictionary. Its columns are basic signals, or they're called atoms. And you want to find how to best represent your signal by a linear combination with most K dictionary atoms. Another application is compressed sensing, and there you have a sparse vector X, and you observe linear projections of it, possibly with noise, and you would like to solve the inverse problem, recover X from these observations Y. And of course, in statistics, we have linear regression or sparse linear regression. We have pairs of observations. Here I change the bit notation, X, Y, and here my unknown is a vector beta, which is d-dimensional, but assumed to be sparse. And I'd like to try to predict Y with at most K variables. Okay. In this talk, I will assume that K is known. Of course, in practice, K is typically unknown and needs to be estimated. So one possible approach is to solve the original problem P0 from many different values of K, and then apply cross-validation or some model selection criterion or something. I will not talk about this. So in this talk, I will assume that K is given. Okay. And I'll focus on trying to solve this problem P0 for a given value of K, given A, given Y. Okay. So the first thing to keep in mind that the main challenge in solving this problem is support detection. If someone tells me choose these columns or these variables, then I only need to solve this first problem. There's no difficulty whatsoever. Unfortunately, finding the optimal support is NP hard. And yet this one is so important that you have really extensive work, algorithms, theory, lower bounds, upper bounds, etc., by vast different communities from statistics, machine learning, applied math, signal processing, etc. I think that just on the algorithmic side, there are at least 100 different methods or variants of methods that try to approximately solve this problem. So what I'll try to do is Of course, also lots of theoretical guarantees. So I'll try to do it in 3 slides. Okay. First, let's talk about the algorithmic side. There are many methods that are greedy. You start from an empty support set and you try to add one variable at a time. And these many papers, this goes back essentially to the 1960s with forward stepwise linear regression. These methods, most of them are very fast, very easy to program. But I'll show you later, they may yield suboptimal solutions when the problem starts to become more challenging. A different approach is which we like very much in statistics, is to replace our non-convex constraint by some penalty. The most, of course, we have this parameter lambda, we need to tune it, and if we want to a k-sparse solution, we need to maybe scan several values of lambda. And of course, the most popular penalty is the Lasso, which is convex, so everybody's happy. And we also have various recovery guarantees for it under various conditions, like incoherence or restricted isometry property or eigenvalue, etc., etc. It's also, by now, there are very, very fast methods to solve Lasso problems, even very large scale. And yet, I'll show you empirically, it may yield highly suboptimal solutions. Okay, now in the last maybe 8 years, as far as I'm aware, there was very interesting work by people at MIT. This paper, for example, they proposed a mixed integer programming approach that when it ends, it finds the globally optimal solution. Okay, and you read the paper, it's very convincing. It solves it globally. And at least if you look at the examples in their paper, they're able to solve problems, let's say, with 100 variables or so, much faster than exhaustive search. But it could be very slow. For example, we took their code, and on a very small, relatively small matrix, we ran this on a huge cluster, and it took us several days. Okay, I'm talking about 30 observations, 180 variables. They significantly speeded up this approach. There's a new paper with the cutting plane method, and this method is able to solve things much larger in, let's say 10 minutes runtime. And yet another recent approach is also by Raoul Mazumder from MIT. He proposed some coordinate descent with a small local combinatorial search. This is a greedy approach. There is no certificate of optimality, but at least his code can handle, 1 million variables in less than a minute. And I would say it's a relatively recent paper with relatively excellent performance. On the theoretical side, we have many, many guarantees. I'm not going to list all of them. Under center conditions, many different people, some of them are here in the audience, have proved that current methods are either optimal if there's no noise or rate optimal. And so you could ask yourself, has the problem been solved? Has not been solved yet? Should someone work on it? And my point I'll try to convince you is that there's still some work to be done. And again, the key limitation, just from the practical point of view, is that as the problem becomes more difficult, let's say as you start to have higher values of k, okay, larger k is less sparse, the problem becomes more difficult. Either all of the methods that I've reviewed, either they will find solutions that are far from optimal, or may take essentially forever to run. Okay, so let me.
How do you understand optimize?
Well, so there are 2 ways. One is when there is no noise and your vector is exactly k-sparse. You want so there are under certain conditions, solving a basis pursuit recovers the L0 sparsest solution. On the statistical side, you add noise and you ask what is you add a statistical model and you ask no. I'll talk about something slightly different because I'm going to have noise that is not random. Just I'm not going to have a random noise. Okay. All right. But just to illustrate the empirical performance of various methods, this is a very simple simulation. Your matrix is 100 by 800, run Gaussian matrix. I'm making the problem harder and harder. Okay, I generate a k-sparse vector X, add noise to it, and try to run various different algorithms. And first, I'm just asking on the optimization side, not even about accuracy of recovery or anything else. Did I get a solution whose residual is smaller or comparable to that of the original x0? Okay, if this ratio is close to 1 or even smaller than 1, then my x hat may possibly be an accurate estimate of x. And if this ratio is much larger than 1, then probably just on the optimization side, I was not able to find a good solution. Okay, all right. So this is the result for the Lasso or basis pursuit. So the x-axis is the sparsity, as you can see. For this specific example, the Lasso essentially works only for sparsity levels less than 16 or so. Okay, because at around 16, it starts to go higher and higher. These two are iteratively weighted least squares, iteratively weighted L1. What? Yes, we'll discuss this lower in a minute. Okay, but let's focus on this region for a minute. Okay. This is iterative support detection, and what I want to show you is our method, which does this. To anticipate your question, in this region, there is overfitting. Okay, there is now the fact that you find a solution with this ratio smaller than 1 does not mean that you were able to find the correct support. Okay, but the focus would be on this region. Okay, so and just to illustrate your point, I'm going to take this k equals 36. This is the average of many runs. So I'm going to show you let's say the 100 specific realizations. So what I'm showing you here is for a sparsity of 36. Now I'm really showing you the reconstruction error, both of our method and of iterative support detection over maybe 100 different realizations. When this ratio is much smaller than 1, so the points that are here, both methods succeeded. All of these points are realizations where our method succeeded and iterative support detection didn't. And these are cases where both methods failed to succeed. Okay, so, all right. Okay, so that was the motivation. And now let's talk about, so our goal is to solve P0, but I want to do it by a panelization approach. Okay, so what would be good properties for a penalty function? Well, first of all, if someone gives me the value of k, the target sparsity, I may want my penalty to depend explicitly on this target sparsity level that I wish to achieve. In terms of my penalty parameter lambda, I would like that when I solve this problem and I take very large lambda, I would like the solution to be close to those of the original P0. And better yet, maybe I would like them to coincide for sufficiently large lambda. And the third property, which is important, otherwise I would not be giving this talk, I would like whatever penalty I suggest to be somehow easy with double quotations to optimize. Otherwise, I didn't do much. Okay. So first, let me discuss a penalty that satisfies the first 2 points. Depends on k, and its solutions are close to the P0. This penalty is called I'll call it the trimmed Lasso. We came up with it, but later we find out that smart people came up with this penalty before us. So you just take like the Lasso, but you just don't penalize the top k coefficients. You just penalize the L1 norm of the tail. Okay, so it's essentially, it measures the distance of your vector to the nearest k-sparse vector. Okay, if your vector is k-sparse, the penalty is 0. Okay. So this penalty appeared in paper by people from approximation theory and people in signal processing. and also in people from optimization, and also in the work by the people from MIT. And they actually coined, at least as far as I know, they coined the name trimmed lasso. Okay. So this is the penalty that we're going to look at. And you can ask various questions. First of all, if you add a penalty of this form rather than the lasso, what is the relation to the original problem P0? What values of the penalty parameter lambda should you use? How well can you recover a vector X if you're using this penalty? And on the practical side, how can you optimize an objective when you have such a penalty? Now, keep in mind this penalty is hard to optimize. It's non-convex and it's hard to optimize. If you have a vector which has k large coefficient and the other one are small, your penalty is the L1 norm of the ones that are small. But if you make a small perturbation and you switch the roles of the kth and k plus 1 or k minus 1, who's become largest, the penalty is highly non-smooth as you perturb X. Okay. So what I'm going to show in this talk is I'll try to address essentially questions 1 to 3. I'll try to convince you that actually you should solve, if you're interested in sparse solutions, you should actually solve problems with the trimmed lasso, but that is typically difficult to optimize, and you should actually use a surrogate penalty that is much easier to optimize. Okay. All right. So here is so the original problem is P0. I'll call this problem P lambda with the trimmed lasso penalty. And the first question we'll ask is how to choose lambda. And here is a very simple lemma that we proved that if you have your design matrix A, you compute what is the largest norm of your atoms, of your columns. And if you take any penalty that is larger than the norm of y times this largest norm of any column, then any local minimum of P lambda is k-sparse. Okay. And what this means is that for large enough lambda, the optimal solutions of P lambda coincide with those of P0. Okay, so you could instead solve P lambda. Of course, this will also be NP-hard. Yes, there's no free lunch yet. It will be maybe later. Okay, but in terms of a strategy, you can think about trying to solve the problem with a set of increasing values of lambda until you get to a k-sparse solution. And this is guaranteed to happen certainly once lambda surpasses that threshold. Okay, now a little bit about a relatively simple signal recovery guarantee that we're able to derive, and this will be related to your question about optimality. You see, my model is that I observe a vector y, which is ax0 plus e. X0 is unknown, is what I want to recover, and e is not random, it's just measurement error. And what I'm going to assume that x0 is approximately k-sparse. So approximately means this, that its distance to the nearest k-sparse vector is much, much smaller than its L1 norm, and I'm going to assume that the norm of E is small. Okay? And the question is, well, my problem, of course, is to recover x0 given A, Y, and K, and the question is, can I do it by solving P lambda? Yeah, we'll see immediately what it means to be small. Okay, but, all right. Now, this problem is, of course, ill-posed because I didn't yet say anything about the matrix A. So, for example, even in the absence of noise and with the supercomputer to be able to recover my x0, I need, or any x0, I need any 2k columns of A to be linearly independent. And what I'm going to assume for my analysis is something similar to a restricted isometry property. I'm going to assume that this requirement, so it's like an RIP, it's one-sided, I don't care about the other side, and it's with mixed norms because that's maybe some of our limitations, but this coefficient alpha 2k, I only need it to be larger than 0, but I don't need it to be bounded away from 0. So this is the assumption I'm going to make. And two more things before I describe the result. One is that notation. If you give me a vector x, I'll define by pi k of x its projection into the nearest k-sparse vector. Okay. All right. So now I want to describe some recovery guarantee with the streamed Lasso penalty. And so I'm solving a non-convex problem. So what I'm going to assume is something maybe non-standard. I'm going to assume that whatever algorithm you employed was able to find a reasonably good solution. So what is a reasonably good solution? I'm assuming that it found a solution whose objective is smaller than that of the projection of the original x0. Okay, so pi k of x0 is a feasible solution. It's k-sparse, and I want to find I would say that my optimization algorithm succeeded if it will find the vector x hat whose objective is smaller than this. So what I'm going to show you is that if this occurred, I cannot guarantee it will occur. I'm solving a non-convex problem, but if this occurred, then x hat or its projection are close to x0. Okay, and this is the okay. So and this is the result. This is the result if x hat is not k-sparse. But let's look at this formula. It's a bit simpler. If x hat itself was k-sparse, then I have a bound on its L1 norm, and it involves two terms. One is how non-sparse, non-k-sparse was x0. If x0 was k-sparse, then this first term would be 0. And the other term involves the error, the norm of E, and also how much x0 was non-sparse. And of course, it's exploded by 1 over alpha 2k. Okay, so this is exactly where how small can the measurement error be. Two important things about this result. It holds for any alpha. And alpha can be arbitrarily close to 0. And I don't need it to be bounded away from 0. Okay. So okay, yeah, this is if x hat was k-sparse. If x hat is not k-sparse, there is a more involved formula which also depends on your penalty parameter lambda. And the important take-home lesson from this formula is that, in fact, I don't necessarily need to solve the problem p lambda with a very large lambda. I may solve it with a lambda smaller than a lambda where I get a k-sparse solution. I may still get a solution whose projection is close to my x0. So I can try to solve my objective with a lambda for which this optimal solution don't necessarily coincide with those of p0, and smaller lambda hopefully is a somewhat easier problem to optimize. Okay, and again, the recovery is stable with respect to measurement error and inexactness of sparsity. In comparison to the Lasso, our guarantees are worse. They have a worse dependence on the inexact sparsity of the x0, but they don't require the RIP constant to be strictly bounded away from 0. We only require it to be just positive, which is a necessary condition for uniform successful recovery by any algorithm whatsoever. Okay, so before I move to the computational part, I hope that I've convinced you that maybe trying to optimize things with the trimmed Lasso is a promising approach. The question now is how to do it. Okay, so this is our objective. And these two papers, they both also consider this objective, and they both propose different methods to optimize it. Both methods don't work so well, at least not on challenging problems. And again, the reason is that this penalty is highly non-smooth. You take a vector, whose coefficients are slowly decaying, you perturb it a bit, the top k coefficients change by a lot. And many of these methods get stuck at some local minima at the incorrect support. Okay, let me show you some results. So this is comparison to DC programming. DC programming was the method proposed in this paper. So I'm showing you results for different sparsity levels. When the sparsity is small, k equals 15, this is an easy problem. Yes.
on the previous slide, I mean, I'm just extrapolating from the title. Is it just to write tau k as the L1 norm minus the sum of the k largest k term? And
Yes.
then it's a difference between two convex functions, and there are good heuristics for this.
Not so good.
Not so good, but maybe in this case it's not so good. But in general, there's some good heuristics.
We took their code or we re-implemented it. I'll show you a totally different approach.
Okay.
Okay.
Because you see, like a good heuristic is to linearize the second one, so it becomes affine. And
yeah, I don't remember by heart what exactly they did. Let me show you what we did. And okay, but empirically, when k is small, it's an easy problem. What I'm showing you here is whether the optimization succeeded. Okay, whether you find a solution which is feasible and has a lower objective than the true solution, then and it's on a logarithmic scale. So anything here is success, anything here is failure, and all of these are instances where our method succeeded and DCP failed. The story with ADMM is similar. When k is small, it succeeds. When k starts to be large, it fails. Okay. All right. So now we come to the last part of my talk, which is how to practically optimize this penalty. And for that, I'll rewrite it in a different way. Okay. So this is the definition of the trim Lasso. But instead, I'm going to write it as follows. Take your vector of length d, go over, choose any possible subset of size k or size d minus k, let's say size d minus k, and sum up its corresponding coefficients, and take the one whose sum is smallest, okay? All right. So this just tells you that the trim Lasso can be viewed as a hard minimum. Namely, you go over all possible subsets and you choose the one with the minimal L1 norm. And our idea is we're going to replace this hard minimum by soft minimum. This is what people in neural networks do all the time. So this will be our surrogate, okay? So you start with your vector x. Right now it's a thought experiment. We're going to expand it to a vector z of length exponential in x, whose coordinates will be, for any subset omega, its coordinates will be the sum of the corresponding entries. The trim Lasso is the minimum of this vector, and we're going to replace this minimum by a soft min. Okay, so this is exactly what people do in neural networks. It's the last layer. It's a softmax formula used in multi-class classification. So here's a softmax of from m categories. We need a soft min, so we're going to add a minus. We're going to add a smoothness parameter gamma, and we're going to average the thing inside. Doesn't matter, just adds a constant. And we're going to plug in the original definition of the huge vector z, and this is our surrogate penalty. Okay, we call it the generalized soft min. So let's see what is my next. Yes. So we are going to replace tau, the trim Lasso, by this penalty, and let's look a bit what are its properties. So first of all, it's infinitely differentiable in terms of absolute value of x. That's good. We'll be able to maybe do stuff with gradients and such. The parameter gamma controls its level of smoothness. We'll show in a minute it has nice properties when gamma goes to 0 or gamma goes to infinity. You can also think about it from a Bayesian perspective. If your target x0 is k-sparse, but you don't know, but you have a uniform prior over all possible subsets where it's k-sparse, you could think about this as your Bayesian prior and add it as and I'll show you in a minute that it is somewhat or significantly easier to optimize. Okay, so some properties about this function. It's monotone decreasing as you increase gamma. And it has a nice properties. If you take gamma to 0, you get the lasso up to a multiplicative factor. And when you take gamma to infinity, you get the trim lasso. Okay, so it actually, you can somehow interpolate between the convex lasso and the penalty that is much closer to the original problem P0 that you wanted to solve. And as I said, instead of optimizing this, we suggest to optimize a sequence of functions with this generalized soft mean, where we propose a homotopy scheme. We start from a very small gamma 0, let's say even 0. For 0, you start from the convex L1 problem, and you start to increase gamma, and you track your solution. Okay, you initialize your new object. You try to optimize your new objective starting from the previous solution for a slightly smaller gamma. Okay. All right. Now, still, as appealing as this may seem, there is a problem because this objective is non-convex as well, and the way we're going to approach it is, again, standard in optimization. We're going to use majorization minimization. We're going to construct a different function that majorizes this penalty. We're going to do a first order Taylor expansion. This is a definition of a majorizer function. It's a function of two variables, and it coincides with the original penalty when the two variables are the same. So if you do majorization minimization, you're guaranteed to decrease monotonically, typically only to a stationary point. I'm not going to go into the details. I'm going to tell you. So these are some ways that are related to the gradient of my penalty. The key point is that you do a first order Taylor expansion, you get this as your majorizer. And what's important about this majorizer is that you have two variables, x and x tilde. So this majorizer, some of these terms are constant with respect to x, and therefore doing a majorization minimization step, you only need to solve a convex weighted L1 problem. So you can just plug into any classical standard solver that is out there, solve this, do several majorization minimization steps, and I'm done. Okay. So this is essentially similar to iteratively weighted L1. There's an important difference that although all my weights are bounded between 0 and 1, they have the same sum. So you don't need how much time? 2 minutes. Okay, I started 2 minutes late.
3 minutes.
I only have 15 slides to go. Okay, so I don't need to regularize, which is crucial in iteratively weighted L1. Okay, the last technical thing, all of this would not be useful if I didn't have a way to compute these terms. These terms involve an exponential number of terms. So if you think about it a little bit, so naive calculation is of course out of the question. If you think a little bit, you will be able to come up with a recursive formula to compute these quantities. It will be highly unstable because you're computing x of gamma times something, and gamma is going to be large. So you need to be very, very careful. I'm not going to go into the details. We developed a scheme that takes order KD operations to compute the various required quantities. So it's not the bottleneck. The bottleneck is solving the L1 problems, okay? And let me show you some results. Let's skip everything else. Okay, I'll show you some results. This is a similar simulation to the one in Hazim and Mazumder, which in turn I think is also similar to the simulation that Peter Bullman had in one of his papers. So you have a sparse signal, the design matrix is correlated, I generate a vector y, it has noise, and I have various measures of success. So this is the coordinate descent method of Mazumder. This is when I add is local combinatorial search, and this is our method. So we're able to recover the correct support with roughly 20% fewer observations, which at least in some compressed sensing applications could be important. This is for a relatively high SNR. If I have a lower SNR, the same picture, just you need more samples to recover the correct support, to be able to do it with fewer observations. I'll stop here before Yankee stops me himself. Okay, so to conclude, as we all know, the sparsity plays a key role in many, many applications. I think that on challenging instances, there is still room for improvement. I think that the trimmed lasso is a desirable approach. I think the approach I described may be useful in other problems involving combinatorial search and sparsity. There is code, there's a paper. Thank you very much.
Thank you. If there is a really burning question, I'm happy to hear it. Oh, and Boaz to answer it.
Hi. Thank you very much for a nice talk.
It's been a long day.
Thank you very much for a nice talk. So my question is, is there any solid theoretical evidence on this trimmed lasso is better than lasso? Say, could you give us some setups where, let's say I can have a infinitely powerful optimizer that just solves the trimmed lasso and a lasso. Just so statistically, is there any case where trimmed lasso is absolutely better in terms of, say, MSE or support recovery?
Are you assuming that you have an oracle that is able to minimize the trimmed lasso? Or,
yes, I assume such oracle.
Yes. So for example, the result, the recovery guarantee that I showed you holds for any alpha larger than 0, and for the lasso, you know that there are dictionaries with alpha small for which the lasso will probably fail.
But how big can be your error? Because the alpha is in the numerator, but you have the error norm in the numerator.
Right.
So what is the SNR that you can work with? The ratio between the AX and...
Yeah. So it depends on how...
Practically.
I didn't work with... I did simulations similar to what previous people designed, and this is what I didn't play with actual data.
Okay.
Theoretical results are not about selection, but about
the theoretical result is assuming K is known.
No, I mean that they are bounds on the L1 error. Yes.
Yes.
And this is not a selection type result. This is estimation result.
Correct. Yeah.
Okay.
Yeah. It's an estimation result.
To your question, I have an answer. In one case, it is minimax optimal. If matrix I is identity matrix, then one can prove that this solution is exactly minimax optimal.
There's a very famous statistical science paper comparing best subset selection and lasso, and also lots of approaches. Basically, the message is that if the signal to noise ratio is high, then best subset selection is better. But on the other end, if the signal is weak, then lasso can be better. So
you're talking about the paper by Tibshirani.
Right. The review paper.
I have some criticisms about the paper, but I'm not to tell them now. But I can discuss it offline.
Sure. I'm happy to discuss. Thank you.
Any other questions? No.
And that's not a question, but
I know.
It's an answer.
let's thank Boaz and all the speakers. I just have a couple of housekeeping announcements. So we have a reception and poster session starting at 5 just outside. You can probably see the poster boards. There is food there. Dinner is tomorrow. And if you registered for the dinner, you should have received an email from Judy McDonald confirming it. If you haven't received such an email, then you probably didn't register. If you can't remember whether you registered or not, you can send me an email tonight. We had a few last minute cancellations, so I do have a few open spaces for the dinner. So if you didn't register, but you changed your mind and you want to go, you can also send me an email tonight about that, but please don't do it tomorrow. So tonight only. I will see everybody tomorrow at 9 o'clock. Thanks.